Right, we are back and we are now looking at derivatives and some application questions, and also in particular Lin and E because they're still fairly new to the syllabus. Okay, all right, so let's have a look at working with the exponential function. Now, if you look at your table here, you go and you find y equals your function e to the x, and the derivative is also e to the x. Now, unfortunately, it will be very unlikely for you to get asked a question of just differentiate y equals e to the x. So you're going to be looking at it in the form of the chain rule where you've got y equals e to a fancy power f of x. And its derivative is going to be e to that fancy power times by the derivative of that fancy power. Okay, so very important that if you've got e to the f of x, when you differentiate it, it remains the same. So it's still e to that same power times by the derivative of that power. So let's have a look at some examples. If I've got y equals e to the x squared plus 1, can you see I've got a fancy power there? So when I differentiate it, it's going to still remain e to my fancy power times by the derivative of my fancy power, which is 2x. Okay, let's have a look at what happens if I put some trig in. So I can say e to my fancy power of sine x. When I differentiate it, it's still going to be e to my fancy power times by the derivative of sine, which I hope you know well, is cos. Okay, all right, let's look at how we can apply this. So if I'm looking at a question where I'm asked to find the coordinates and nature of any stationary point for this particular curve, what am I thinking? Well, stationary point, I'm thinking derivative equal to 0. Okay, and when they ask me about the nature, I'm thinking, okay, well, I need to either establish whether it is a minimum turning point or a maximum turning point or even a point of inflection. Okay, so let's have a look. And what do I do? The first thing I'm going to do is I'm going to differentiate it. Now, when I look at this expression, it is the product of two algebraic expressions. So I'm going to apply the product rule. How does the product rule go? Differentiate the first, gives me 1. Leave the second, e to the minus x, plus leave the first, and then differentiate the second expression. So what have I got here? E to the negative x. So it's e to my fancy power times by the derivative of my fancy power. Okay. All right. That gives me the gradient function for any point on that curve. I want to know what happens at the turning point is where the derivative is equal to 0. And I can then see, okay, I'm going to take out a common e to the negative x, and I'm going to neaten it up. Now, you can leave it in this form, or you can write it as a rational function by taking e to the negative x downstairs. It's up to you. Okay, but if I've got it in this form, I'm going to then say either e to the negative x equals 0, which it can't, because the exponential function can't equal to 0, or my bracket is equal to 0, or if I've got it in this form here, then I can say clearly for a fraction to be 0, my numerator needs to be 0. Okay, that gives me the x value of my stationary point. So what do? I sub it into my original to get my y. All right. Unfortunately, we don't end there because it says determine the nature of the stationary point. There are a lot of people that like to work out the second derivative and decide what happens when it's positive or negative. Okay, I always find that if it's in factorized form or if it's in rational form like that, it's much easier to just stick those values on a number line and test the gradient. So if you look here, I put 3 onto my number line, okay, because that's where my 0 is. I test a value bigger than 3 anyway, either there or there, and I find that I'm going to get a negative over a positive, so my gradient is going to be negative, and if I sub in a value less than 3, it's going to be positive. Okay, which means that if you think about how I would draw this, my graph is going to be increasing. And what's going on here? It's going to be increasing, and then when I get to 3, it's going to be decreasing. Okay, and so therefore, what can I say? There is definitely a local maximum. All right, now let's go on to what happens when we're working with Lin. All right, so again, looking at my table, I've got my function y equals ln x, and its derivative is 1 over x. Okay, now again, chances are you're not going to get asked to just find the derivative of y equals ln x. It's going to look like y equals ln f of x, some fancy expression here. Okay, and so then what's my derivative going to be? 1 over my f of x, my fancy expression, times by its derivative. Okay, so let's have a look. So if I've got f of x equals ln of the algebraic expression x squared minus 3x plus 1, what do? It's going to be 1 over that same expression times by the derivative of that expression. Okay, so a nice kind of way of thinking about it is that the denominator is my f of x and my numerator is my derivative. Okay, all right, so let's see how we can apply that. So if I ask you to find the gradient of the normal to the curve y equals ln x cubed minus 5, can you see I've got a fancy f of x here at the point where x equals 2. So first and foremost, I need to understand that normal, the normal is the line perpendicular to the tangent. Okay, how do I get the gradient of the tangent? I differentiate and I substitute 2 into x's place. Okay, so let's differentiate this. So what have I got? I've got 1 over my expression x cubed minus 5, and what happens at the top? Or I times it by the derivative of my fancy denominator of 3x squared. Okay, I then want to know what happens at x equals 2. I sub it in, and that is the gradient of my tangent. Okay, now remember that the normal is the line perpendicular to the tangent. So what do? We change the sign and we flip it over. Okay, if I'd asked you to find the equation of the normal, I then remember to get the equation of any line, you need a gradient and you need a point. I've got my gradient, I've got half a point. So how would I get my other point? I would then substitute 2 into my y and have my point. Okay. All right, let's have a look at some other application questions using derivatives. So if I look here, I've got a trolley is moving in a simple harmonic motion about the origin. The displacement s meters of the center of the trolley from O at time t seconds is given by, and here I've got a formula for my displacement. Okay, and the question is find the velocity of the trolley when t is equal to pi over 6. Okay, the first thing I look and I go, velocity is change in speed, change in distance over change in time, or more formally, the rate of change of displacement. So that means it's going to be the derivative of this function. Now, the minute I see a power, so do you see I've got sine squared? I'm going to rather write s of t as sine 2t to the power of 2. It just makes it easier for me to say, okay, right, I'm going to definitely use my chain rule now. Okay, so let's have a look at our table. The chain rule, remember, you're going to hop this down, your bracket's going to remain intact, and then you're going to times by the derivative of the bracket. That's what that little formula means. Okay, so if I s dash t it, I differentiate it, what am I going to do? I'm going to drop the 2 down, my sine 2t remains the same, and then I differentiate the bracket. Okay, and what's the derivative of sine? Cos 2t, my angle also stays intact, and then I differentiate the angle, gives me 2. Okay, I neaten that up, and I could go further, but it just asks me to find the velocity when t equals pi over 6. So I'm going to substitute pi over 6 into t's place and get my answer of root 3. Now, because they're asking you for a velocity, you follow it, especially when it's in a contextual question, you follow it with the particular unit. So it's meters per second. Okay. All right, this is a wonderful question, okay, because it's not so much a differentiation question or using derivatives, it's actually going backwards. So look here, you are given the second derivatives 2x plus 2, and you have the point 1, 10 over 3 is a turning point of f of x, find f of x. Okay, now if ever we want to go backwards, so we want to go from the second derivative to the original function, if we're going backwards, we're going to find the antiderivative. And the antiderivative is integration. Now, obviously, you're going to do harder integration a little bit later today, but let's look at, so if I'm going to go, if I've got the second derivative, if I want to find the first derivative, I integrate that function, which hopefully you can do in your sleep, and you're going to have x squared plus 2x plus c. Okay, now before I can integrate this again to get my f of x, I need to know the value of c. So in order to get the value of c, I need to substitute a point in so that I can get c. So what information are they giving me? That this is the turning point. Okay, now the turning point means that when x is 1, the gradient is 0. Remember, this y value has got nothing to do with my gradient. Okay, and this says f dash x. You only substitute this point in place of a y value. It is not an f dash value. So what happens at a turning point? My gradient is equal to 0 when x is 1. So what am I going to do? I'm going to replace 0 in place of f dash x, and I'm going to put 1 in x's place, and I can get the value of c. So my first derivative is now looking like that. Okay, then what do? I'm going to integrate now this expression to get my f of x. Okay, and I'm going to now add on a different variable for my constant just to kind of emphasize that it's not c, which we know to be -3. And so I now need to find the value of k. How am I going to find k? I have to sub in a point. Now this is f of x. So this is my y and that's my x. So what is this? This, yes, it's a turning point, but it is also a point that sits on my curve. So I can then substitute in, and I can replace x with 1 and y with 10/3 and find the value of k. And hence, my function is now f of x equals to that expression there. Lovely, hey? Okay. Now, let's have a look at this one. This is also an application question of using your derivatives. I want you to try and draw this graph before you see a picture of it, okay? So I want you to pause it and give it a good go. But let's just have a look at what all of these concepts mean. So this derivative less than 0 means I'm going to have a decreasing function. The second derivative is less than 0, means it's concave down. Now remember, concave down means the curve is below the tangent. Okay? F of 0 is 20. Well, hopefully you all know that that means when x is 0, y is 20. And then when x is 2, y is 0. And f of 3 is less than 0 means that when x is 3, you're going to get a negative y value. Okay, so I want you to pause and then have a look, try a graph it and see if it looks like mine. Okay, you should have done that. Now, let's have a look at what my graph should look like. Okay, so let's start with the easy ones. When x is 0, y is 20. When x is 2, y is 0. And when x is 3, it is below the y-axis. That's all I'm interested in. Okay, now, and look at this first part here, and it tells me that it's where the derivative is less than 0. Okay, so that means it's a decreasing function. Now, I don't know if it's going to decrease like that, or if it's maybe going to decrease in that shape. Okay, so what actually makes me go this way is that the graph also tells me that it is concave down. Okay, now concave down means that if I take any tangent, okay, and I draw the tangent, you can see that the curve is below the tangent, and I can go anywhere along there. The tangent, the curve is always going to be below the tangent, and so we say that it is concave down. Okay, I hope that makes sense. All right, the next question is, a drug is given to a patient and the percentage of concentration of the drug in the bloodstream t hours later is given by the function k of t equals 5t over t squared plus 1. So t is in terms of hours. Okay, when is the concentration increasing and or decreasing? They could ask you probably either one of those. Okay, now, as soon as where is something increasing or decreasing, I'm thinking gradient. And where it's gradient, it's the derivative. Okay, and also, as soon as I have a derivative that is increasing or decreasing, I'm also thinking I'm going to put it on a number line. Okay, so let's start with the derivative. So the derivative of this expression, you can see you're going to apply the quotient rule. So if you remember, what do? You square the bottom, you write the bottom upstairs, you differentiate the top. Minus, leave the top, differentiate the bottom. Okay, I hope you can all do that. You then multiply through, and we factorize the top so that we can stick those values on a number line. So I now put them on a number line because I don't want to know where it's equal to naught. I don't want to know what the gradient is at a particular point. I want to know where is it increasing and where is it decreasing. And a number line will tell me that beautifully. So I sub in my zeros, which would be 1 and -1, and I plot, substitute in a point greater than 1, and I can see that it's going to be negative, positive, negative. Okay, now just looking at this graph, you would say, or this number line, you would say that it is increasing between -1 and 1. And I can promise you most people will write that. But if you go back to the context of the question, it says T is in terms of hours. Now, you can't get a -1 hour. Okay, so where is it going to be increasing? From 0 to 1, and then where is it decreasing? After the first hour. Okay, you obviously could use interval notation there, but I just chose to put it in words. Okay, all right, this is a question that for some reason everybody hates, okay? And it looks worse than it is, but actually it's quite nice and easy. All right, so if you look at this, given the composite function f of g of x is equal to 2x squared plus 3x minus 2, and you're given that information, the first question is find f of 4. Okay, so if I've got, so I want to find f of 4. Okay, so I look and I see what can I work with. Okay, I know f of g of x is equal to 2x squared plus 3x minus 2. I'm going to write f of g of x in this form. Okay, all right, now I look and I see, right, what other information can I do? Don't look at the question, okay? Look and see what can I get from the question, from the information in the question that will help me here. So I can see that it says g of x, and I go here and I go, g of 2. So that means that I could put 2 into x's place all the way through the sum. Okay, so I'm going to put 2 into x's place, and I'm going to end up with 2 squared is 4, 2's are 8, plus 6 minus 2. Okay, and now say, okay, hold on, g of 2 is equal to 4. So I can see that f of 4 is going to be 8 plus 6 minus 2. Okay, looks much worse than it is. Hey? All right, then I do exactly the same thing with the derivative, f dash 4. So again, I start with f of g of x is equal to 2x squared plus. Now remember, I want to get the derivative. Okay, so if you go to your little table, if you remember in the table that I put earlier, the derivative function of the chain rule looks like that. Always write it out. Okay, it just helps you to get information from up here. Okay, so the first thing is I'm going to say the derivative of f of g of x is the derivative of that function, which is just 4x plus 3. Okay, so I've written it on this side, but it really doesn't make a difference. And so I've just swapped those two around, and I've then got f dash g of x, g dash x equals to the derivative of my composite function, which is 4x plus 3. Okay, now I look and I think, what information can I get from the question? Okay, so I go back, and can you see there's a common x value of 2 here? So I'm going to put 2 in x's place right through the sum. Okay, so I've got f dash g of 2 times g dash of 2 equals 4 2's are 8 plus 3 is 11. Okay, I can then go and say, but hold on, g of 2 is equal to 4 and g dash 2 is equal to 5. And I'm left with what I want, which is f dash 4 is equal to 11 over 5. Okay, if you need to go through that again, obviously just rewind and recap that, but actually it looks worse than it is. Okay, implicit differentiation. When you see a curve that has a whole lot of x's and y's in, you know that you are going to use your implicit differentiation. Now, these questions can be up to 10 marks, so they are worth getting correct. Okay, now basically, what are we going to do? So we've got to find the equation of the tangent at the point P1 naught to the curve. Okay, so now if you remember, how does implicit differentiation work? When we come to a term that has an x in, we just differentiate normally and we carry on. But if we differentiate a term or anything that has a y in, we then drop a dy dx alongside it. Okay, so let's have a look. Okay, so what have I done here? I have differentiated this first thing. So I've got 12y cubed. Because it's a y, I drop a dy dx. Okay, plus 4x, the derivative of 4x is 4. Okay, now if I look at my next term, it's made up of x squared or minus x squared and sine y. So it is going to require me to use the product rule. Now be careful with the product rule. If you've got a negative inside in front of your first term, put a negative, open the bracket. Otherwise, you're going to make a silly mistake with your signs. Okay, so we've got minus. We're now going to differentiate this using the product rule. So how does it go? Differentiate the first. It's x, so no problem. Leave the second. Sine y, no problem, because I haven't differentiated anything yet. Plus, leave the first term, x squared. Differentiate this. Okay, so I start by saying differentiating the trig, cos y. Remember, when you are differentiating the trig, the angle follows. Then you times by the derivative of the angle, and the derivative of y is 1. And then you drop your dy dx. Okay, I hope that makes sense. Minus, now I've got an exponential function. So I've got my 4. And then what's the derivative of e to the y? Well, it's going to remain e to the y because the derivative of y is 1. Okay, and because I'm differentiating the y of 1, I drop a dy dx. Okay, this dy dx does not come from this e to the y. Okay, it comes from then differentiating the power function of y, which is 1. Equals the derivative of a constant is 0. Make sure you go all the way through. Many people forget that the derivative of a constant is 0, even though it's quite easy. Okay, now, unless the question states, find an algebraic expression for dy dx, okay, which means that you would do it like this. You would then simplify it. You would then get all your dy dx terms to the left and everything else to the right, and you would then divide through by that, and you get a nice algebraic expression or mixed with trig here. And then what do you do to get your dy dx? You sub in the point 1 naught. So in other words, instead of x, you put 1, and instead of y, you put naught, and you get your gradient to be 4/5. Okay, you then want to find the equation of the tangent. So now you've got the gradient, plus you've got the point, so you just follow your rule. Okay. Or I want to show you a quick way, and that is once you've got to this point here, okay, if I just am asking you to find the equation of the tangent, in other words, I just want you to find the gradient, I would actually substitute this point in as soon as I've done this first line. Okay, so in other words, at this point here, I'm going to sub in the value 1 naught all the way through. Okay, so I'm going to show you it. So I'm going to put naught in y's place, and I'm going to put 1 in x's place all the way through. Okay, and you can see now this whole term falls away. The sine of naught is naught. This whole term falls away. The cos of naught is 1, so I'm left with that is a term, and e to the naught is 1, so that is a term. So look what I'm left with. I'm left with 4 minus dy dx, which comes from that. So minus times a plus is a minus 4 dy dx equals naught, and it just means that I've got less room to make silly errors when I'm doing all that algebra. Okay, and then I get my gradient to be 4/5, and from there I can go straight into finding the equation of my tangent. Okay, so this is just a quick way. Obviously, you can only do this if they say to you, if the question is such that it is, show that dy dx is that expression. Well, then obviously you have to show all the steps. Okay, but if I just want to get a value for the gradient, I'm just going to sub in right from word go. It also saves a lot of time. Okay, let's have a look at this next question. It's saying what is dy dx at the point, so again, what is the gradient at the point 2, 1, and you've got the function y squared minus 1 equals ln x minus y, if dy dx exists. So in other words, I don't need to put any restrictions on, okay? It's already told me it exists. Okay, so I look at this again. I've got x's and y's in, so I'm thinking implicit differentiation. So I start and I go, right, let's start with the first term, 2y. Because it's y, I drop to dy dx. Minus the derivative of a constant, 0, equals. Now, be careful here, okay? You've got ln x minus y. So the derivative of that is 1 over x minus y. Full stop. You haven't differentiated a particular y function, okay? So it's 1 over x minus y times by the derivative of that denominator, and the derivative of x is 1, minus the derivative of y is 1, but because it's 1, because it's y, I drop a dy dx, okay? So be careful of that. People tend to make silly mistakes with those steps. Okay, I am going to not find all the terms of dy dx. I'm just going to sub in straight away to 1. And I put, instead of y, I put a 1. And instead of an x, I put my 2. Okay, and I solve for dy dx. If you want, you can even put m in place of dy dx. And I end up with my gradient equaling a third. Okay, so you guys just need to practice, practice, practice. Implicit is worth lots of marks, but just also all your other derivative rules. Please just practice these.